In this video abstract, I will introduce you to the paper Dephasing rephasing dynamics of one-dimensional tunneling quasicondensates. In this paper, we study two tunneling quasicondensates considering two different configurations. Configuration A represents side-by-side tunneling quasicondensates, where the atomic tunneling occurs along the whole length of the system, with a tunneling energy J perpendicular. In the system configuration B, we model a system of two quasicondensates in a head-to-tail configuration, where tunneling occurs only in the middle, with a tunneling energy J parallel. What happens if a single quasi-condensate is quickly split in configuration A or B, and tunneling between the subsystems is restored by lowering the potential barrier? The relative phase between the subsystems will be initially zero and will then evolve in time. In our paper, we show how the phase coherence evolves by calculating the coherence factor, C of t, defined as the average of the cosine of the relative phase phi at time t. With some calculations, the coherence factor can be rewritten in terms of the sum over the standard Gaussian deviation of the non-interacting quasiparticles which constitute the system. Since these sigmas are oscillating in time, also the coherence factor oscillates in time. So, with respect to the non-tunneling quasi-condensates, which the phase, as you can see in the orange dashed line, we find the dephasing and rephasing oscillations of the coherence factor. We observe this behavior both in the side-by-side tunneling quasi-condensates and in the head-to-tail parallel quasi-condensates, due to a qualitatively similar excitation spectrum. In a temperature range of some nanokelvin, which is an order of magnitude lower than that of the current experiments, these oscillations are not thermally dissipated and can be observed. Thus, following the interplay of experiments and theory, we hope that our work will increase the understanding of the phase dynamics in quantum many-body systems.